I'd like to talk about these problems out of section 1.8 on page 269. I'm going to change the instructions when we get to 25 because it actually has the same instructions as a few of the other problems, and I just want to make things a little more interesting when we get to it. So to start here, problem number 8 off of page 269 gives us two functions, f and g. F of x is the function 2 over x minus 5, and g is the function 2 over x plus 5. The instructions tell us to find f composed with g and g composed with f to determine whether each pair of functions are inverses of each other. So I have f composed with g, an outside function, 2 over something minus 5, and then g of x goes on the inside. Well, I have a plus 5 and a minus 5. I can lose those parentheses, and they cancel. I have 2 over x. So I multiply fractions by changing the division symbol to multiplication and taking the reciprocal of the bottom. 2 times x over 2 is just x, and that's what we're supposed to get if these are inverse functions. We still need to check the composition in the other direction. So this time the outside function is the function g, 2 over something, plus 5. And this time the something is 2 over x minus 5. All right, so this time I have 2 times the reciprocal of the bottom, plus 5. Well, the 2's cancel. I have x minus 5 plus 5 is x. I get x with both compositions. F and g are inverses. All right, next up, problem number 16. Problem number 16 gives me one function and asks me to find its inverse and then verify it doing the thing we just did. So number 16, my function is 3x minus 1. We'll start by following our simple process to find inverses. We write this down in terms of y, and then we swap x and y. And I like drawing a line there because the moment I swap x and y, I'm now talking about an inverse function. Add 1 to both sides. Divide everything by 3. Finally, I should write that as an inverse function. All right. Part B asked me to use function composition to make sure I got it right. If I was just asked to find the inverse function, I'd stop here. I would not check my answer this way unless told to, which I was, so I will. All right, f is the outside function. Let's plug f inverse in. Distribute the 3, and I get x plus 1, still with that minus 1 on the outside, and that gives me x. So first step's good. F inverse is 1/3 times something plus 1/3, and the function f goes in there. And when I distribute that through, I get x minus 1/3, still with that plus 1/3 on the outside, and I get x. And everything's all well and good there in number 16. 17 comes with the same set of instructions. This time the function f of x is called x cubed plus 2. So again, we write this down as an equation with a y in it. We're going to swap x and y. And then we're going to get y by itself. This time we have to take a cube root, write it down as an inverse function. Please don't skip this last step. If you go through all this trouble, you might as well write the formal statement at the end that says you got it right. Part B asked me to check my work. So I need to find f of f inverse. Well, when I cube a cube root, I get the thing on the inside. And I've written that wrong. That was a minus 2. All right, good catch. Plus 2. X minus 2 plus 2 is x, and that's what we were looking for. This time I have the cube root of something minus 2. Plug in the function. Plus 2 minus 2 cancel. I have the cube root of x cubed, which is x. And those really are inverses of each other. Next up, we have problem number 25. And I think I mentioned that I wanted to change the instructions up when I got to 25. Because it has the same instructions as the book as the other two, the 16 and 17 that we just did. And so I thought, maybe, just maybe, we could look at something different this time. So in number 25, we're given the function f of x equals x plus 4 over x minus 2. And this time for part B, instead of doing what's in the textbook, I want to find all the domains and all the ranges. Because there's a neat trick that we can use to find domains and ranges. In fact, I could go on and write down the domain of f here without even breaking a sweat. The domain of f is everything except for the number 2, because I can't divide by 0. Just from looking at this, I have no idea what the range of f is going to be. I don't know. I have no idea. We're going to have to talk about that in a minute. But let's find the inverse function in part A, because we were asked to. And then maybe things will make sense over here. So I write it down as a y equals. I swap the x's and y's. Now I'm supposed to get y by itself. So I'm going to multiply both sides by y minus 2. I think about cross multiplying here, really. Distribute the x. If I'm supposed to solve for y, I need to get everything with a y on the same side. So I'm going to take y away from both sides. And I'm going to add 2x to both sides. And now I can factor a y out. And then I find out that y is equal to 2x plus 4 divided by x minus 1. And that's my inverse function. I went through the arithmetic a little different in my handwritten solutions. I get the same answer for both, so it's worth checking out. All right, I can write down the domain of f inverse with no problem. Because it's also this fraction, I know I can't divide by 0, so I have to throw 1 out. And then I remember, the domain of the inverse has to be the range of the function. So because domains are easier to find, sometimes I can find a range of a function by knowing the domain of its inverse. And vice versa. The domain becomes the range, and the range becomes the domain. All right, so that's what I wanted to do with 25. You can compose f and f inverse and f inverse and f and show that these are really inverse functions of each other. I have 2 more problems I want to do. And in the video now, apparently you're going to hear drilling because we're in a construction site here at Alamance Community College, so I apologize for that. But I'm going to press on and go on and do problem number 36. 36 shows me this graph. Graph neater because your author used a computer to generate it, and I've drawn it by hand, and wish I had done a little bit better of a job there, but it's okay. And on that graph are emphasized 3 points. So I got minus 3, 0. I have minus 1, 2, and over here I have the point 5, comma 3. And the instructions are to use this graph to graph the inverse function. And all I have to remember is that the x's and y's swap. So if the point minus 3, 0 is on the function, the inverse function has to contain the point 0, comma minus 3, which is right here. All right, minus 1, 2 is on the graph, so 2, comma minus 1 has to be on the inverse. And then finally 5, 3 becomes 3, 5. my handwritten solutions contain a nice picture where I actually used a straight edge, so that'll come out a little nicer than this one. But there's my graph of F inverse. And though we're done with the problem as stated in the book, I thought we'd take a minute to write down domains and ranges. Just to emphasize a point, the domain of F is everything to the right of -3. The range of F is everything greater than 0. So even if I hadn't graphed its inverse function, I could write down its domains and ranges because they swap. The x's became the y's and the y's became the x's. And that's all I really need to know to write down these domains. Now it's nice that this right graph, all the x's are from 0 to infinity, and all the y's from -3 to infinity. So I could have gotten domains and ranges from the pictures or from each other. That was number 36. One more problem from the textbook. Problem number 44 out of section 1.8. Number 44 asks us to find an equation for F inverse and then to graph F and F inverse in the same rectangular coordinate system, and then finally to find domains and ranges for both. Number 44 here, I'm given the function f of x equals x minus 1 squared, where x is greater than or equal to 1. I'm going to start by graphing that function. It's the graph of y equals x squared shifted to the right 1 unit, but only for the x's larger than 1. You can plot a few x's and get a nice picture that looks like this, but that's y equals f of x. All right, I'm supposed to find the inverse's equation and graph it. I'm going to go on and graph it. I'm not even going to wait to graph it. I'm going to go on and graph it because I can just swap some ordered pairs. This is the point 1, 0. So the point 0, 1 is on the inverse. This is the point 2, 1. So the point 1, 2 is on the inverse. And this is the point 3, 4. So the point 4, 3. That has to be the graph of the inverse function. I know inverse functions are symmetric with respect to the line y equals x. So if I fold those two over, they'll lay down on top of each other. Everything looks great there. And I recognize this. Let's see what happens when I find the inverse function. First up, I swap x and y. And the moment I do that, I see that y is going to have to be greater than or equal to 1. And I see that in the graph I've already done. Y is greater than or equal to 1. I need to take a square root. And just for a moment, I'd think about maybe a plus or a minus. But if I know that y has to be greater than or equal to 1, then that has to be a plus. Because if y is bigger than 1, take 1 away, I still have a positive number. That's going to have to be a plus. So y equals root x plus 1. That's my inverse function. And look at what I've graphed here. That's the graph of a square root function shifted up 1 unit. That is that nice, happy graph. And that's the end of the problems from the textbook that I wanted to do. But right now, I want to do one more. I'm going to call this 44 plus. And it's the same instructions, but I want to see what happens if we were told that x had been less than or equal to 1 instead of greater than or equal to 1 in that last problem. So I still have the graph of y equals x squared shifted to the right 1 unit, but this time it's the other side. And again, we could think about plugging in some x values to get a pretty good graph here. And so here's the graph this time. It's the other side of that parabola. And I could go on and do the same thing I did last time where I graphed the inverse function first. This is the point 1, 0, so the point 0, 1's on my inverse. The blue point here was 0, 1, so 1, 0's on my inverse. And this is the point minus 1, 4, so 1, 2, 3, 4, minus 1. Those are my that's my function and my inverse function, and symmetrical around the line y equals x, absolutely. Fold over that line, the blue becomes the red becomes the blue, they lie on top of each other. So let's find out what I just did. Swap x and y. Take a square root, and again, just for a moment, I'm going to worry about it being either a plus or a minus. And this time I'm told that y is less than or equal to 1, which means I'm taking something smaller than 1 away. So, excuse me, I'm taking 1 away from something smaller than 1, so it's going to work out to be a negative number. Y equals minus root x plus 1. That's my inverse function. If I think about my transformations of functions, that means reflect the root function over the x-axis and then shift it up 1. And that's what we've graphed there in red. All right, those are the things out of section 1.8 I wanted to talk about. My handwritten solutions are posted to Moodle.